Today, what we're going to do is reformulate everything, but using the nomenclature that we'll be adopting for multi-component mixtures. And this is where things get fun and interesting and significantly more challenging. So I'm going to jump around a little bit from how I've had my notes in the past, try and cut out all the stuff that's not particularly intriguing, kind of go just to the core of it. So hopefully I don't mess up too much. Now, we've heard the term, or hopefully everyone here has heard the term ideal system or mixture. Now, what we mean by an ideal system is more or less that we can write the properties where the total, let's say, internal energy or some other property of the system is simply equal to just adding up the number of particles of species I multiplied by the individual internal energies. We can also write this as the total molar volume, total molar property of the system would be equal to the mole fractions times by, just divide this by n, right, in this case. Just some mole fraction. Everyone should be familiar with mole fraction, I think, just in case. Mathematical definitions. Another one to look at here is that the total molar volume of the system is just adding up the volumes of the individual components. This is going to apply for particularly internal energy and volume, and it will also apply for enthalpy as well. For entropy, this is not going to be the case. Entropy will be generated when you have a mixing process occur. Now, for a real system, we have a delta mixing property. In this case, what we'll be writing for the most part is we'll do everything generalized. Where I'll use this theta nomenclature for any molar property, enthalpy, Gibbs, Helmholtz, internal energy, volume, not temperature and pressure because those are not molar properties. So the property change upon mixing is going to be the final system property, right? This could be, let's say, internal energy. That's going to be a function of temperature, pressure, and the nomenclature that I'll use is this xi, or it's xi with a little underbar under it, basically saying, let's see, do I use that? No, I don't use that too much, not the underbar. The xi here means that this property is a function of the mole fraction of every single component. So the total Gibbs of a particular system is a function of temperature, pressure, component 1, component 2, component 3, component 4, component 5, component 6, and so on and so forth. So we can get very complicated very quickly. Minus what we would expect from ideal mixing alone, in which case this molar property subscript I corresponds to a pure component. That's only going to be a function of temperature and pressure. So this here is the ideal mixing contribution. This is the non-ideal final result. The difference between those two is, let's say, what is the volume change of mixing? What is the heat of mixing? Is it endothermic? Is it exothermic? Does it expand? Does it contract? That's effectively what we're saying mathematically here. I'll do a graphical representation in just a bit on this. So if it's ideal mixing, we have no property change. We just dump everything into a bucket, and they all behave as if they're all alone. So one definition that we'll use is we want to take this function here and try and break it down into a little bit more manageable bites. Because right now this is some sort of an abstract arbitrary function. So the total mixture property, again this could be volume, internal energy, is the total number of moles in the system multiplied by the total property, the molar property of the system. Now very generally, this is a little bit abstract, let's imagine we have some magical function that is a function of temperature, pressure, number of moles of component 1, number of moles of component 2, number of moles of component 3, number of moles of component 4, and so on and so forth. This function, hypothetical function, is one that we would really like to understand. Because that's going to tell us how do we minimize the Gibbs, maximize the entropy, minimize the enthalpy, right? This is going to tell us the function that we have to manipulate in order to understand what the phase equilibrium is going to be. But it's going to be clearly very complicated because it's a function of everything. So instead, what we're going to do is we're going to, what we can do, rather, is we're going to take the partial derivative of this property with respect to some component in the system holding temperature, pressure constant, and all the other amounts of all the other compounds. So this is I not equal to J. The subscripts get a little bit tedious when we get to multi-component systems. So effectively, we'll be taking a partial derivative of this massive arbitrary function, which will involve using the product rule. So we take it with respect to temperature, holding everything else constant. Take it with respect to pressure, holding everything constant. And 1, 2, 3, 4, 5, and everything along the way. So skipping over a lot of somewhat tedious mathematics. As you can see, I'm going through several pages here of notes. We come to a particular conclusion that is very helpful. We find that we can write the total molar property of the system, and this is going to be a function of the temperature, pressure, and composition. Right? This is going to be total Gibbs, this is going to be total enthalpy, this is going to be total internal energy, total volume. We can write that as a summation of this function here. And what we do is this partial derivative, we define this as a new thermodynamic property. So what this allows us to do is it allows us to write out the total molar property of the mixture. This is the property we care about when we put it into the second law or the first law of thermodynamics. This is a function of temperature, pressure, and all of the components in the system. So it's a big, very complicated function. And what we've done with this sort of mathematical substitution here is that we can then write this as the summation, breaking it down of individual partial molar properties. Now, one thing to keep in mind is this is a little bit of a mathematical trick to make it simplified. You'll notice that the total property of the system, let's say volume. Volume is an easy one to think about. The total volume of the system is dependent on temperature and pressure, obviously, right? Composition, right? If you mix water with, I'm trying to think, ethanol, does it expand or does it shrink? I don't remember.
It contracts.
It contracts with ethanol? Yeah. So, for example, you can mix it with ethanol, but how much it contracts is going to be a function of how much ethanol is in the system. Whereas on this side here, it's also a function of temperature, pressure, and the total composition. So when you're thinking about a mixture, and if you mix ethanol and water together, you cannot say with certainty that it's water's fault that the volume changed, or that it's ethanol's fault that the volume changed, right? Because all of the partial molar properties are a function of the system composition as well. But this partial molar property becomes very important if we look at the partial molar Gibbs. In this case, this is oftentimes referred to as the chemical potential. This is going to be equal to the total change in the Gibbs of the system with respect to changes in composition of component I. Oh, there's a subscript needs to be here. At constant temperature, pressure, and composition of the other components. Now in thermodynamics, they like to adopt this nomenclature of the chemical potential because it's very generalizable. The partial molar Gibbs is the chemical potential that we most often use because it is being held at constant temperature and pressure. We can rewrite the chemical potential, and we will do that today, for a system at constant pressure and entropy, or a system at constant volume and entropy. Those are going to be different forms of the chemical potential. But this is the one that we care about the most. So despite the fact that this is somewhat of a cyclic logic, we're taking some arbitrary complex function that's a function of all of the properties of the system. We're rewriting it now as a summation of some arbitrary complex function. But as it turns out, this arbitrary complex function is super useful for phase equilibrium. So we'll hopefully get through all of that today, unless I totally botch what I am trying to get done. Graphically, just do a quick overview of the concepts and also of the nomenclature. So if we have a system, and so oftentimes now we're dealing with multi-component systems, we like to kind of draw two y-axes, one for pure component 2 in this case, and one for pure component 1. So if you write this as the mole fraction of component 1 in the system, so all the way over here, this is pure component 2, so this is x of component 2 is equal to 1. This is the mole fraction of component 1 equals to 1. Over here, this would be the property of pure component 2 that's only a function of temperature and pressure. Some property up here would be the value for pure component 1, which is only going to be a function of temperature and pressure. Let's say this is volume. If this is an ideal mixture, the volume should be a straight line. I didn't do that perfectly well, but it should be a straight line connecting the two. In which case the ideal mixture is just the weighted average of the pure species properties. And I like to kind of continue to for at least a little bit, continue to remind us that the pure species are only functions of temperature and pressure. But in reality, the volume may change, right? It may be some sort of an arbitrary function that looks something like this. With mixtures, basically anything's on the table. The real system properties can change a lot. It can be unexpected. There can be lots of curvature changes, a lot of inflection points, right? There's a lot of possibilities. This will be the real mixture properties, in which case the line is given by the summation of the partial molar properties. So it adopts a very similar notation. One thing to note for the nomenclature that we're going to be using, this is the Sandler book nomenclature, so I don't know how well it translates to other texts. We draw a line underneath it. That's going to be a pure component system or the total system property. Right? It's only going to be function in the case of a pure system. Right? You'll note that we have an underbar with a subscript I, meaning that we wouldn't have bothered to put the subscript I unless it was going to be in a mixture. Right? The underbar with the I means it's probably only going to be a function of temperature and pressure. Underbar without the I is going to be temperature, pressure, and composition. Overbar, subscript I, means that it's going to be the value, partial molar value of that property in the mixture, so it's going to be temperature, pressure, and composition. So the overbar is always going to correspond to the mixture property. Underbar is a little bit confusing, differentiating between whether or not it's the total system or the individual, but hopefully it's be clear in the context. Now the difference at any point here right? The delta property change upon mixing is a function of the composition because you can see the magnitude is changing based on where I'm considering what the property change upon mixing is. So one of the most convenient ways that we can write this this is not a 100% mathematically appropriate way to think of the system, right? The math is fine here, this is appropriate. So the difference, the change of mixing, like let's say the change in volume or the heat of mixing, right? It's just going to be the difference between how the molecule behaves in the mixture versus how the molecule behaves with itself. So if the volume or the density of a fluid is about the same, if you change its surroundings, then you say it's more or less an ideal mixture. Now this is not a 100% strictly way to think about it because you cannot isolate any single component and say it's your fault that the volume is changing, it's your fault that the enthalpy is changing. Right? So the classic example is sulfuric acid and water. Is it really sulfuric acid's fault that a lot of heat is released when you mix it with water? Or is it kind of water's fault because it accepts all those extra hydrogens or protons? Right? It's not clear who's the one actually at fault in that particular system. But this is a nice, compact, easy way. Oh, sorry, I need a subscript I there. All right, so you're just adding up the differences between the partial molar property and the pure system property. It's a nice, compact way to think about it. Using this definition here for the partial molar property is very convenient because it effectively allows us to rewrite everything that we've already done in exactly the same way. The only difference is we just go from an underbar to an overbar. So for example, if we take the partial derivative of the total Helmholtz energy we substitute in the definition that Helmholtz is defined as U minus TS. Note that we're holding temperature constant here. That means we can basically rewrite this as, so this is the definition of the partial molar Helmholtz. We can just rewrite this simply as the partial molar internal energy minus temperature times the partial molar entropy. So everything is the same. Same thing with partial molar enthalpy, which is going to be equal to partial molar internal energy minus pressure times partial molar volume. Same thing with Gibbs. Partial molar enthalpy. And it further extends basically partial molar heat capacity everything is exactly the same. Nothing's changed. The only thing that's different is now we have this very silly line on top of our functions as opposed to on the bottom of the functions. But it makes the mathematics. So it makes the formulation very convenient, but coming up with these functions is not trivial. That's going to be the big challenge. So when we try and take an equation of state and predict some of these properties, it gets a lot hairier, more or less. Last thing, if we have an ideal mixture, right, we said this cancels with this, and our delta of mixing is equal to 0 if it behaves the same in the mixture as it does as a pure component. Now, as more or less everything looks exactly the same, our energy balances, our entropy balances, those are exactly the same. Just a slightly different nomenclature. So if we look at our general energy balance, now, hopefully everyone, can you all write the energy balance instantly off the top of your head? Entropy balance, instantly off the top of your head. That's going to be your starting point for every question on the quiz, most likely. Not 100% guaranteed, but our focus on the last homework was energy and entropy balances. So if you don't know what to do, write the energy balance. Write the entropy balance and start to simplify it. You will get some points for starting the process. Okay? So there will be certain generalities. So anything that involves an energy balance, write the energy balance. Anything, so any process with flow streams in and flow streams out, your starting point is very likely going to be an energy balance or an entropy balance. Moving forward, when we apply multi-component, multi-phase systems, your starting point is not going to be an energy balance. It's going to be having the fugacities be equal, because that's the phase equilibrium criteria. So I just want everyone to sort of build these tracks in their minds. When you look at a problem, think of it as, am I calculating the properties of a process, in which case you should all use energy and entropy balances. If I'm asking you to calculate the properties of a fluid, what's going to be your general starting point? What about the last problem in the homework? Where we calculated the change in internal energy of a van der Waals fluid. What's your starting point for a property or a state change calculation?
Equation of state.
So an equation of state plus...
Is that the delta U equal?
Yeah, that's one of the forms of the combined first and second law.
Yeah.
Okay? So those are basically, every single problem that you did was one of those two types. It was either a combined first and second law problem or an energy and entropy balance problem. Now that we're moving into phase equilibrium, for single component, the starting point is going to be the fugacity of, we don't need a subscript high, let's say phase 1 is equal to the fugacity of phase 2. What we're going to be showing in the next couple of days is that for multi-component systems, we're going to have a thing called the partial fugacity of component 1 in phase 1 is equal to the partial fugacity of component 1 in phase 2. And this is going to give us Raoult's law ultimately, right, where we're going to talk about the right, so then what we're going to basically be doing is deriving Raoult's law, saying this is the partial fugacity of an ideal gas, this is the partial fugacity of an ideal liquid mixture. So that's going to be the ultimate goal. So when we talk about phase equilibrium, this is going to be your starting point here. And that's really the only 3 types of problems we have in the entire class. Processes, state changes, multi-component, multi-phase equilibrium. So with the energy balance, when you get your quiz, write it down immediately. Summation of all of the different flow rates So the only difference now is in if these streams here are multi-component, you will just have to substitute, in this case the I, maybe I'll change it up, how about this is J. Let's change the nomenclature here. Whereas J are each individual streams coming in. You just have to then consider that each stream has its own enthalpy. But you have to think back into the days of old that if you had a mixture, you don't know that a fluid's a mixture, right? You just know that it has an enthalpy, and you can determine what that enthalpy is based on measuring its heat capacity and choosing a reference state. So the only difference between the energy and entropy balances is that each of the individual streams that come in, you have to then consider that they might be made of individual components. Same thing with the entropy balance. And I could rewrite this in a condensed form, so I'll sum it over all of the J streams, which are then being summed over all of the I components. Actually, sorry, I think no, this is fine. This is fine if I write it this way. Sorry, I was just double checking to make sure that my units are all working out here. Yeah. But I'm sure you could write this a different way if you wanted to in terms of whether or not you want to consider this N or X, for example. Okay. So nothing changes at all except we've got a little bit funky nomenclature. Now the convenient thing about that as well is that that means our equilibrium criteria are identical. Like I said, I'm jumping around a little bit, so hopefully I'm not messing it all up. All right. So let's talk about equilibrium because that's the whole point of all of this. So very similarly to how I mentioned that an equation of state is so much more than just saying, oh, okay, what's the pressure or what's the temperature of this fluid at this state, right? The reason why we care about equations of state is not to do those sort of menial tasks. Same reason as why we're not defining all of these partial molar properties here just for the sake of doing calorimetry or change in density, right? We're using all this information because it's related to equilibrium. Okay, the first and second laws have not changed, which means that our equilibrium criteria is exactly the same. Meaning that in an NVE system, maximum entropy is our criteria. In a NVT system, Helmholtz is minimized. In an NPT system, the Gibbs is minimized. Everything else is exactly the same. Okay, so what we're now going to do is set up our equilibrium criteria. We'll talk about the partial molar Gibbs and the chemical potential. So what we're going to do now is we're going to expand the Gibbs, just exactly like we did with single component, but now we have this additional complication where we have an arbitrary number of molar components or molar species in the system. So that means our change in the Gibbs free energy, actually no, this is not partial, this is the total change in Gibbs, is equal to the partial with respect to temperature, holding pressure and composition constant, plus the change in Gibbs with respect to pressure, holding temperature and the composition constant, plus in this case now it's a summation of the change in Gibbs with respect to the number of moles of species I, in this case holding temperature, pressure, and all of the other species constant. So, through thermodynamic identities, this is a thermo identity here, this is a thermo identity here. That similar ones should have been derived on your homework. And then this is our definition of the partial molar property. And so we call this chemical potential. I think we'll get through all this. Okay, so we're going to do exactly the same thing now, but with the Helmholtz energy. But instead we would expand it with respect to pressure, entropy, and composition. Those are the native units of enthalpy. Same exact procedure. Now remember, again, this is all just general calculus. Taking the total differential of a function means that you have to keep accounting of how that function could change with respect to all the other variables in the system. In this case, our variables, we have pressure, entropy, and an arbitrary number of components. So we need to expand our system with respect to those variables. With identities, we can rewrite this. Sorry, some of these lectures, this is unfortunately one of those less pleasant of lectures where we just kind of go over the rigor. Okay. So you'll notice that I did not replace this with the partial molar property because it is not the partial molar property. Okay. In this case here, we need to be very clear that the change in enthalpy of the system with respect to changing its composition at constant temperature and pressure, again, I don't know how much longer I'm going to keep up these i's not equal to j's, is not equal to the change in enthalpy, change in the composition at constant pressure and entropy. So one last step before we can kind of reach the, I don't know if it's a particularly profound conclusion, but it's a nice conclusion. We can write the Gibbs. Gibbs is defined as the enthalpy minus temperature times entropy. So we can expand that and rewrite this as so all I did was take the derivative here and then kind of rearranged it mathematically a little bit, right? dg is equal to dh minus tds minus sdt. Move everything to the other side of the equation. Solve for dh. We're going to take this definition of the Gibbs here, substitute it in that expression. We're going to take that enthalpy expression here, substitute it into that expression. And what we find actually, no, we're not going to substitute that. Sorry. Skip that step. My bad. We're going to compare the two at the end. Where is it? That's minus SDT. Minus SDT plus EDP plus Marshall Gibbs. Okay, so which ones cancel? That cancels with this. Okay, so we're there. We've made it through. So here we go. So looking at DH, so comparing DH to DH, we have that our VDP is VDP, TDS, TDS, and then this last term here is exactly equivalent, or it must be equivalent, to this last term here. Now with that, I've been too lucky with that thing. So we can rearrange this. We're going to do exactly the same thing that we did last time we looked at this equilibrium criteria. We're going to say that the change in number of moles of component 1 is in phase 1, or component I rather, is going to be equal to the negative of what is lost in phase 2. The change in volume of phase 1 is equal to the negative of the change in volume of phase 2. The change in internal energy of phase 1 is equal to the minus of the change in internal energy of phase 2. Then if we write that the total entropy change of the system is 0, which is equal to the change in entropy of phase 1, plus the change in entropy of phase 2. We do all of this, we do all the substitutions. Right, if you recall last time, that meant that temperature of 1 equals temperature of 2, pressure of 1 is equal to pressure of 2, and now we've got this criteria here for the multi-component system. And here we have our most important conclusion for the entire class, more or less. That if we have a means of calculating the partial molar Gibbs for a particular property, then we can use that to solve all of our equilibrium criteria questions. So now the challenge is going to be how do we accurately predict this? Well, the good news is that we can with an equation of state plus something called mixing rules. So for example, how do the A and B parameters of, let's say, the van der Waals equation of state change as a function of the mixture itself? Now, for a gas or a low density fluid, we can do this reasonably well. We can actually tune an equation of state for compounds that are of similar properties, and it does a reasonably good job. That's because in a gas, the molecules are very, very far apart. So the correction to ideal behavior is relatively minor until you get to really high pressures, for example. For a liquid, equation of state, completely inaccurate. Mixing rules, completely unacceptable. So instead what we do is we introduce something called an activity coefficient. The reason why we do that is because we don't know what else to do. So the most accurate activity coefficient models, what they've done is basically measured the mixture properties, liquid-liquid phase behavior, vapor-liquid equilibrium, vapor-liquid-liquid equilibrium, calculated or measured experimentally what the composition of the two phases are, back calculated what this hypothetical activity coefficient would have to be, and then correlated it. So what we've done is we've done a very elegant, rigorous derivation of thermodynamics until we determine a function or a property that is physically too difficult to accurately model. But the good news is that all of this rigor in thermodynamics allows us to have a framework that helps us categorize and organize data. So it still tells us the minimum number or the types of experiments that we have to do in order to understand what is critically necessary to measure and put in a book. So we don't have to put every property for every state under every circumstance, right? But we now know that we can measure something called an activity coefficient. Who here has heard of an activity coefficient before? Okay, most everyone should have heard of this in an undergraduate course. But basically, this is where things get a little bit less fun mathematically and less elegant mathematically, but they get a lot more applied. So now I'm going to have to talk about real systems. This mixture of this component and this component behaves in a certain way. That's because we don't have an accurate way to do this. Now, there are some reasonably good activity coefficient models, but for example, this is all kind of ad hoc type analysis. For a particular system, there's an activity coefficient model that's tuned for it. All right, out of time, quiz on Friday, so please send me a message if you have any questions on the homework. I'll post the solutions after the official deadline so that everyone can look at it. Please look over the solutions. One note about how I view quizzes and exams. A good example is the Rankine cycle problem. If I give you a cycle, that's for example the Rankine, and you understand it, then I assume you understand all cycles. So refrigeration cycle, Otto cycle, those are all fair game. Right? Same thing with state changes. So if I ask you to do a state change of internal energy with the van der Waals equation of state, I would say it's very appropriate for me to give you a state change with entropy with the virial equation of state. I don't expect that you would have to have seen the equation of state or you would have to be familiar with it, but you'd have to know what's temperature, what's pressure, what's volume, what's the functional form of that. Right? So I'm not so concerned about the actual problem itself, but really be self-critical on do you understand all of the facets of the problem. and not just did you get to the answer. Getting to the answer is only the starting point. So be really self-critical that you understand exactly why every single step along the way occurred, because I'm going to assume that if I asked you a question about state changes with one fluid, then it's totally fine to do it with a different fluid or a different equation of state or a different state change. It's the mechanism of the math that I'm more concerned about, just to be clear. So be self-critical. Do I really understand this problem? All right, see you then.